Welcome back, everybody. I hope you had a relaxing break. At a minimum, at least a break from this class. So a couple of housekeeping items, and then we'll go ahead and get into our review. So all the homework's graded, all the attendance grades are posted, and all three exams up to this point are graded. That is a typo, by the way, because let me, that's a typo. That's a typo. There we go. Sorry. I'll explain that here in a bit. Okay. So what I want to do today is the following, and I'll go through some housekeeping here in a bit. But as I mentioned before Thanksgiving break, I said I don't really have anything else to teach you in Engineering 213. We've covered it. We've covered everything we needed to cover. But I am a firm believer that what causes you to learn this stuff is to do it. Okay, and so I've curated 5 review problems that we're going to do that are somewhat challenging. But if you understand these, you will definitely understand what you need to understand on the exam. And I'll get to the details about that here in a bit. Everybody get the code? Okay. It is our last week. And so I typically like to start the last week with a little bit of housekeeping just to make sure that everybody is aware of where we're at, where we're headed, so that we're all crystal clear on things. Okay? So attendance grades. 10% of your grade is attendance in this class, and the attendance grades for the last, everything before Thanksgiving break is up to date on Blackboard. Okay? There are 3 attendance grades left to do, today, Wednesday, and Friday, and then that will be your attendance grade in Engineering 213. Okay? What about the homework assignments? Everything that's required has been graded. All the solutions are posted, all the grades are posted. Homework, required homework is done in Engineering 213. I do have one bonus assignment. Okay, and the bonus assignment is for you to upload proof that you've done your course eval. I take that very seriously. Any suggestions that you have for future times, either I offer this course or somebody else offers this course. I do really enjoy teaching statics, but it's also a really important class. Hopefully that has come through over the past 14 weeks. But if there's any suggestions that you would have for future improvement of the class, I really would appreciate that you do the course eval. And so to encourage that, if you upload a screenshot that you did, I don't want to see what you wrote. Again, you could say that Dr. Mike is a poopy head and he's the worst professor ever. But if you just show me that you did it, I'll add 10 points on top of your homework average. Okay, and I'm going to have that close. The reason I'm having it close on Tuesday is because that's the day of the final. So I figure at that point, the class is, I guess, officially over. What's left? So today we're going to do a big old course review and probably start into our review problems, and then the rest of this week is just review problems. To be clear, this is not meant to get in the way if you all have any questions about the class or any concepts on the exam, because this is sort of like an exam review week, so don't hesitate if you've got questions and whatnot. As for the exam's on Tuesday, December 10th, 10:15 to 12:15. It is comprehensive, okay? But the logistics are the same, but because it's comprehensive, the exam's just longer, okay? I'm designing the exam to sort of be 100 minutes long as opposed to 50 minutes long, and so I'm using that rule of 3, and so it's going to be sort of double the length of the other exams, so, sort of think in that regards. And it's going to be comprehensive, and it's going to include friction, okay? Because that's one thing we haven't tested on yet is friction, okay? All right. Sound good? Okay. So with that, everybody get the code?
Can you bring it back up for 1 second?
I suppose, and I'm going to do this. I got to throw some jokes in there, though. Everybody got the code? All right. Okay, this slideshow is probably the longest single slideshow in the entire course, which is the course review. That makes sense. But I got a lot of stuff in here that I want to talk about. But I'll break it up into 3 areas. I've got the logistics, what the exam's going to cover, and then some advice that I have for you before we get into our problems. So let's go through the logistics first. Like I said, it's going to be kind of like a double length exam. The exam will be paper-based, just like all the others. It's not through Blackboard, all that. Closed book, closed notes, but you're allowed a formula sheet. Bring a straight edge, all that. The one thing is, for this formula sheet, make it yourself. I'll say one thing about this exam. This exam is not intended to be the most difficult problems of all the previous exams. If anything, the opposite, okay? Because it's comprehensive, I don't believe that these problems are among the most challenging of each topic. But really the challenge is that I'm testing you on a lot of things. So the problems themselves, I think, are pretty straightforward. Don't put anything tabulated like the centroid tables. If any of that stuff, I'll give you. The other thing is, I'm going to let you keep the formula sheets once this is all over. You know how I usually take them up. I'll probably just give them a once over and you can have them back when it's all done. So just make sure that you put the time in necessary to develop it. Let's talk about what's covered on the exam, okay? And so this is what's the topics on the exam, and it's basically everything that we've talked about in Engineering 213. So the fundamentals, make sure that you understand classical motion, make sure you understand Newton's 3 laws, make sure that you can compute the weight of an object. Remember we deal in forces, we don't deal in masses. Make sure that you can convert units and perform dimensional analysis as appropriate, although that hasn't really been the biggest deal in this class because once everything's consistent, it doesn't really matter. I would say that the 2 real math skills necessary for this exam and for this class are algebra and trig. If you can do algebra and trig, you're pretty good. I mean, there's a little bit of calculus here and there, and I don't know if you consider vector cross products calculus or not, but I consider it more algebra than I do calculus, but that's just me. In terms of topics related to this class, okay, so particle statics. Make sure that you understand the properties of vectors, the tip-to-tail addition, and so on and so forth. That vector addition is commutative, a plus b equals b plus a, all that. Make sure that you can add vectors, and make sure that you can apply equations of static equilibrium to concurrent force systems. So if the forces all meet at a common point, there are no moments, okay? And so you do need to be able to solve 2x2 and 3x3 systems if needed, so that does lend thought to the idea of bringing a calculator that can do that for you. I got no issue with any calculator that you use as long as it doesn't have a Wi-Fi connection. Rigid body systems, so being able to compute dot and cross products. Make sure that you can compute moments in 2D and 3D. Make sure that you can resolve force couples. And make sure that you can compute moments about an arbitrary axis. And all that stuff is really trying to get to this, which is being able to generate an equivalent force system, taking a bunch of forces and simplifying it into a smaller, more manageable system of forces. But really, our goal is equilibrium. We want to try and figure out what are those unknown reactions necessary to keep the system or the structure in equilibrium. And this is no real different conceptually from a particle statics problem, other than that we now have moments. Because we're not dealing with a concurrent force system, we're dealing with a non-concurrent force system. So because the forces don't all meet at a common point, we have to ensure that translation and rotation is prevented. What's left? Centroids, structural analysis, and friction. So centroids, make sure that you can locate the centroid of a line, an area, volume. Make sure that you can compute the moment of inertia of a given region. Structural analysis, make sure that you can compute support reactions, make sure that you can compute internal forces in members of plane trusses, either with the method of joints or method of sections. Although the method of joints is far more tedious, it's more thorough. And that you can construct shear and moment diagrams. And finally, this is the new one, problems involving friction, so make sure that you can determine equilibrium conditions for things in contact, which is That's basically one way of saying just make sure you can handle all the friction stuff that we've talked about in class. And then past this, I've got my references. So this is relevant formulas and expressions. And really all this is if you go to the exam review slides for exam 1, exam 2, exam 3, this is just all those slides all in one place. So if you go to Blackboard and download the slides for lecture 41, this is like 90 to 95% of all the formulas you'd ever need on the exam. I'd venture to say this is probably all of them. So make sure that you understand weight equals mass times gravity, basic unit stuff, trig preliminaries. I am going to go through this kind of fast because you've seen all this. Trig preliminaries, make sure that you understand the basics of vectors, vector addition, how you can split a vector up into I and J or I, J, and K components. The vector expressions in 2D and 3D. This is bringing it back, and it's been a while since we looked at a lot of this stuff. Let's see, cross products. So the two ways that we can produce or compute cross products. The dot product, that one's pretty easy. We only used the dot product like once. That was for a moment about an arbitrary axis. The formal definition of a moment is R cross F, which R is the position vector from the point in question to the line of action of the force, and then F is just the vector defining the force. Or you can use FD for the magnitude, F being the magnitude of the force, and D being the moment arm, the shortest distance from the point in question to the line of action. Moments in 2 dimensions, we often dispense with the vector notation and just do Rxfy minus Ryfx. And again, FD still applies. We can do a moment about an arbitrary axis if we take R cross F and dot it with lambda, lambda being the unit vector along the axis in question. Or if you only want to do it in one calculation, just do it as a big old determinant. That works too. Force couples. So a force couple is if two forces have the same magnitude, parallel lines of action, and then opposite directions separated by some distance. That's a couple. So you can split that up into a single moment vector. What's the deal with an equivalent system? The idea is that two systems are equivalent if they have the same sum of forces and the same sum of moments, but typically what we're doing in an equivalent system problem is taking the number of forces and moments and making them smaller. We want to make the problem more manageable, so we're trying to do this. Now in equilibrium, we're setting the sum of forces and the sum of moments equal to 0 and solving for unknown reactions. I will tell you, just like on the last exam, same thing with the final, I'm not going to get inventive with, here's this short length system that has a reaction 30 degrees that way. I'm not doing that. It's going to be straightforward stuff that you've seen, pins, rollers, fixed supports, things like that. Same thing with 3D. Nothing that's out there. Basic stuff. Like mainly the ones we'll deal with are like ball and socket, or ball and socket here, a ball type connection, or maybe a cable and whatnot. That's about it. Moments of area, so we have that if we integrate dA, we get the area, and then we can integrate x times that, get the first moment or the second moment, and so on and so forth. And where theirs were valuable is the first moment of area. If we take the first moment of area and divide it by the area, we get the centroid. And the second moment of area is, in fact, the moment of inertia. Really, what you're going to need to be able to do is this. And again, any of these references that you need, I will give you. I won't expect you to come up with that on your own. Same thing with 3D centroid references. Anything you need, I'll give you. The parallel axis theorem for the moment of inertia, that's if you want to take that centroid problem a step further and figure out the stiffness about a given centroidal axis. And again, any of those references, I'll give you. And then the method of joints, method of sections, then all our relationships for shear and moment. I'll skip past that because I think this is a little bit more fresher in your head. This is our pattern for concentrated loads. This is our pattern for distributed loads for when we're constructing shear and moment diagrams. And then lastly, this is the new stuff, static and kinetic friction. And so just make sure that you understand, the difference between F sub m and F sub k, and that friction always opposes motion, and things like that. Whew, that was a lot. But we've done a lot in here, so we've covered a lot. All right, any what I would say logistical questions on the exam, because we're going to get to some like review topics here in a bit, but any just questions about how the exam's going to be formatted, about what to expect on the exam? Anybody nervous about the exam? Okay, good. That's what I want to hear. Okay, I wanted to give you some advice and some suggestions for the exam. Mainly, a lot of this comes from, I've been grading the past 3 exams, and I want to see, I'd get tickled if everybody in here got 100. And so I want to give you some advice for how to do well, and maybe not just on this exam, but on all exams. But this is just the stuff that I've noticed, not just this semester, but in my entire, 10 plus years of being a professor. This is the stuff that I've noticed that I'm telling you that I think will help you as you negotiate the exam. Okay, so first off, time management is key, okay? But I would focus on the problem weights. There have been times where there's a 4-point problem and I see this 2-paragraph answer and I go, it's 4 points, move on, you know what I mean? So don't spend too much time on a problem that isn't worth much, okay? I would say read the problem and answer the problem. Don't do more than is required. And the other thing is, if a value is given to you, use it. If there's a 3D problem and there's a vector given to you, don't try and derive that vector if it was given, One big one is to show work. Put stuff on the page, because the more you can give me, the more that I can potentially award partial credit to, okay? Don't put stuff on the page, is basically what I would say. It's usually not a bad idea to independently repeat your calculations, do the calculation in your calculator and then do it again, because if you get the same answer, that means that you're not getting calculator error. And on the last exam for the centroid problem, that was pretty rampant, not because everybody was doing something bad, it's just there's a lot of calculations in a centroid, a lot of individual button crunches on a centroid problem. And so a lot of the mistakes were just, 6 times 7 equals 36, just not because you didn't know what you were doing, it was just this, So doing the calculation and doing it again. One thing I would say is don't make a problem more complex than it already is. And I want to say something about this in relation to the second exam. This might be a bullet that you might want to review what you did on the second exam, mainly with now that we've got a little bit more experience with some fresh eyes. So, as an example, the last problem on the second exam required you to sum moments. And a lot of folks were doing that in vector notation. I bet if you were to take that last problem on the second exam and just do it again, you probably would go, oh, I could just do this and not have to do vector notation, and I would still get the same answer. So there's probably a better, easier way to do some problems. Does that make sense? You don't have to be does every problem need to be done in IJK notation? Probably not. So just that's what I would probably do is that. Don't skip steps. I say problems 6 and 7 because of how I numbered them in my spreadsheet, but maybe I should say 3 and 4. Maybe I should say 3 through 4. Oop. I'll say 3 through 4 on I just sort of number them sequentially in my spreadsheet, but don't skip steps. So if you're doing a truss analysis, if you don't compute the support reactions and just go straight to the truss analysis, you're probably going to get something wrong in the truss analysis. So don't skip steps. Go through the process. There were some folks who just didn't draw the moment diagram on problem 4 on the exam, or on the last exam. You kind of needed to do that. So don't skip steps. Okay. Now, I put that bullet twice. I don't know why I put that bullet twice. This is probably my most important piece of advice. make sure you study topics that are more ubiquitous. And the ubiquitous is a really fancy word for saying stuff that shows up a lot. For example, if on the last 2 exams you had a problem with computing support reactions, that's something you should study. Because support reactions, that's going to show up a lot. It's going to show up for truss analyses, for shear moment diagrams, for just there might be a problem, just compute the support reactions. And so if you have trouble with that, that's a skill that you really want to develop. I mean, like, don't get me wrong, a moment about an arbitrary axis uses skills that show up a lot, but we had that lecture and then we moved on, you know what I mean? But reactions, we've been doing reactions for a while. So I would try and focus on the topics that just show up a lot, okay? Because, you know, use your time wisely, okay? All right. Does that make sense? All right, any questions on that? Okay. So, would you all like to do some review problems? Okay. So, I have collated, I spent a lot of time on this over break because I wanted this to be a good set of review problems. I have collated 5 problems. These 5 problems, I've designed these problems to try and utilize as many topics in the course as possible in these problems. I've tried to package that as much as I can. I want to be clear on 2 things. Okay, the first, I can't cover the entire class in 1 week, so I'm missing some stuff in these problems. So, like, there's no force couples, okay? I guess you could say there's not really an equivalent systems problem, even though I kind of think that bleeds into a lot of the stuff that we're doing here, but I'm not covering everything, okay? But I think with these 5 problems, I am covering the vast majority of what we cover in this course, okay? And the second point, I really want this to be said, in my opinion, these problems are hard, okay? In fact, I think these problems are more difficult than any of the individual exam problems we've had this semester. And I also think that if you understand, but there was a point to that. If you understand these problems, you should understand what's going to happen on the exam. So I wanted to push the envelope a little bit on these problems. Because if you're going to be here, let's make it worth it. Okay? Does that make sense? So I'm going to give you a taste of the 5 problems, and then we're going to get into each one. So let me show you problem 1. So problem 1, we're going to determine the tensile force in these 2 cables, but I've got a lot of different forces being applied. Okay? So this is just a really big bookkeeping problem. Problem 2 is probably the one I had the most fun with. So problem 2, we have a plate that has a roller support, a ball and socket support, a cable. There's a 300 Newton force, and then there's an edge moment of 200 Newton meters. And we have to figure out the reactions due to all this. That one's new. We have a centroid problem, which I think is a little involved, and we're also going to do a moment of inertia calculation on this one as well. And so we haven't done a moment of inertia calculation with circles, okay? And then I'll show you the other 2. So I could not resist doing a truss problem. This truss problem I think is pretty straightforward, but there's a result on one of the members which may be a little surprising, and so I really wanted to throw that in here. And then my 5th problem, this one's my second most fun. So this one is we have a beam that is being supported at A, and it's being held in place by friction right here. And so we need to figure out what the load is, the maximum load that we can put on the beam before it starts moving, and then we're going to draw the shear and moment diagram for those loads. So, like I said, I made them challenging. So, but again, we're pushing it a little bit with these. Okay, is that fine? All right. So let's see if we can at least knock out the first one. Let's see if we can do that before we call it for today. Because I was planning that we might not even do a problem at all, but we'll see if we can knock out this first one. Okay, so I have here a particle, so this is so does everybody recognize that this is a particle statics problem, right? Because we have a series of forces that are all meeting at a common point through point A, right? So if we want to do our free body diagram, so if we want to draw a free body diagram, maybe right here, let's do it in green. So we've got a single point right here, point A. It's going to have that force. That force, we'll call this FAB, FAC, and then there's going to be, bless you, 3 forces that are applied. And our goal is to figure out the forces inside these 2 cables to keep the system in equilibrium. Okay? Make sense? So, we obviously want to use a graphical approach, right? Remember all that law of sine, law of cosine stuff? That was a joke, not a funny one. This is one of those problems where I believe that IJ notation would probably be the most opportune way of going about it, right? So we have 5 vectors, right? So let's see. Maybe we'll use the board a little bit. So we have FAB, FAC, F1, F2, F3. Right? And so what we'll do is we'll say a pile of junk times I plus a pile of junk times J and we'll dispense, at least here on the board, and say that all forces are in newtons. So we'll just not worry about writing units here on the board. We'll just put the values in where they go. Okay. Sound good? So, let's see if we can reason through at least some sign stuff here on the board, just to get a global picture. Let's talk about AB. Let's talk about force AB, okay? Is this going to be negative or positive? What about this? Positive, right? So this is going to be negative. This is going to be positive, right? Sound good? Okay. All right. This is going to be FAB. FAB. Does that make sense? We have to have the magnitude in there. And what am I missing? What goes here and what goes here? What about this one? What goes here? The cosine of 60 degrees. And then what about here? The sine of 60 degrees. It is, all right. This is your review time, so I want to make sure that you're comfortable with this. Is everybody okay with this? Okay. All right, what about FAC? Let's start off with the signs. What's the deal? They're both positive. Both positive. So FAC, FAC. Okay. We got to figure something out here. So let's look at this right here. So this is 5 and 12. So if that's 5 and 12, what does that make the hypotenuse? 13. Okay, so what goes here and here? What goes here on the X? And here?
5/13.
Is everybody okay with that? Is everybody okay with that? Okay. Let's talk about F1. And I'm going to put this stuff here on the screen here in a second. But what's the deal with the signs?
They're both negative.
Negative. Bless you. Okay. So if they're both negative and this is 45 degrees, tell me what I put like here and here. There we go. So this is 120 cosine 45, 120 sine 45, right? Make sense? Okay. F2, this one's easy. What goes here and here? 0 and negative 200, right? And then this one, what's the deal with the signs? Positive and negative, and so this is going to be 40 times something. Okay, so what is that something? That something is, let's see. So this is 8 and 15. Somebody know if it's an 8 and 15 what the hypotenuse is? 17. That's a Pythagorean triple, so that's 17. Okay, so that makes this, what does that make this? That makes this 15 over 17. That makes this 8 over 17, right? Okay, let me put that here in the notebook here. Oh, my notebook's not liking me right now. I might have to copy this in the notebook later. Let me try this again. My notebook's not liking me. Let's try this. You know what? I'll just worry about this. I'll copy it in the notebook later. We're making good progress here on this problem, and I don't want to get in the way of that. Okay. All right, let's do this. Okay, so you tell me what to do. What do I do here? Let me scroll up here. Tell me what to do. Some forces. So remind me, how do I do that? Like, what am I, when I say some forces, like, why did I write it this way? Add all the stuff for the I's, add all the stuff for the J's. Okay? And so we'll just do that and that. Okay? And by the way, let's see something here. I'm going to do a little bit of math here on the side. The cosine of 60 degrees is what? 1/2, and the sine of 60 degrees is √3/2, right? And then the cosine of 45 degrees is the same thing as the sine of 45 degrees, which is √2/2. Is that fair? Or I'm going to do an improper fraction because I just am. Okay? Is that good? So let's see what we've got here. Let's do the sum of the forces in the x direction. Let's do the x direction first. Okay? So what do we have? We have negative FAB times 1/2, right? So maybe what I'll do is I'll put the negative inside the parentheses. Okay? Plus FAC times 12/13, right? Minus 120, was that 120 over √2? plus 40 times 15, that's 600 over 17 equals 0. Is that fair?
Wouldn't that be 120 times root 2 over 2?
Well, that's true, but 1 over root 2 equals root 2 over 2.
Oh, okay.
So I'm just being lazy.
Gotcha.
So is that fair? So what do we got? We've got FAB times minus 1/2 plus FAC times 12 over 13 equals 120 over root 2 minus 600 over 17. So we'll call that equation 1. Is that fair? You tell me. I'm letting you all run the show. So, okay. So now we'll sum forces in the y direction. Okay. So what do we have? We have FAB times the sine of 60 is root 3 over 2 plus, let's see, FAC times 5/13 and then minus 120 over root 2 minus 200 minus 40 times 8, what's that, 320 over 17. Is that fair? Okay. So FAB times root 3 over 2 plus FAC times 5 over 13 equals 120 over root 2 plus 200 minus 320 or plus 320 over 17. Okay. So I'll transpose this to the notebook here in a bit, but the reason I'm doing it this way is because I can do this in Excel or your calculator or however you want to do this. So what do we have? We have minus 1 over 2. We have, so see what I'm doing here? I'm going to write this in matrix notation. So here, let's write it in matrix notation over here. So what do we have? We have minus 1/2. What is that? Root 3 over 2. And then what do we have? 12 over 13, 5 over 13. And then equals all this, so 120 root 2. I get that sine root 2. Did I get that right? Did I get that right? I think I did. So So we can replace this stuff over here on the right with just 49.559 and 303.676. Anybody have an answer? Anybody get that? I'm just curious. How many of you have done this? Because everybody brought their Casio FX 115 ES Plus or similar scientific calculator, right? Y'all remember this? So if you do this in your Casio, you should get something like X is 263.438 and Y is 196.384. That's what you should get. Anybody get the set? Anybody get that? I want to make sure I did it right. We'll say FAB. Anybody match me? Okay, we got a match. Okay. What do we think? I just sort of blazed through this one, but how are we feeling about the process? Is this too difficult? Is there anything that I go too fast? Anything that you want to go back and look at? Anything that was confusing? I'll copy this into the class notebook a little later. I'll do that later. But I wanted to make sure we just sort of went with it. So far, so good? Okay, I want to take at least a second and look at the next problem. So just so everybody's aware, this is, I think, when it starts getting like really challenging, maybe this problem. Because this one's got stuff you've never seen before, this whole edge moment thing and how we handle that. But I want to be crystal clear that this is no different than really any of the other problems that we've dealt with. We just sort of treat this as additive to all of our moments. But this problem is going to take us a little while because we're going to have to do some cross products. We're going to have to break everything down. But I guess before we leave, I want to see if we can at least agree on a strategy. So we have a 100 kilogram plate subjected to a 300 Newton force and a 200 Newton moment as shown. So what do we have to determine? We have to determine the reaction at A, the reaction at B, and the tension in cable C. So essentially what we're being asked to find are the reactions. That's what we got to do. We got to find the reactions. Okay. So how many reactions are we going to have here at A? If this is a roller. How many reactions are we going to have at C? If it's just a cable. It's just a tension in a cable, just one. How many potential reactions are we going to have here? In 3D. If there's a ball and socket joint, we could have a force in the X, Y, and Z. right? It's a 3D pen, so we can have reactions in all directions. So I guess my question is, we're going to have to, this is an equilibrium problem. So we're going to have to sum forces, and we're going to have to sum moments. Now, if this was a shear and moment diagram problem, you would have to sum moments as well to find reactions. And one of the things that we ask ourselves is, about which point do we sum moments? So I guess my question to you is, for this problem, if I'm going to start doing a lot of cross products, I have to sum moments about a point. What point should I pick?
B.
B. Because that's where all the unknowns cross, right? So write my R vectors like from here to here, here to here, here to here, here to here, right? Does that make sense? We'll pick this problem up next time. We don't have time to get into this next time. And by the way, this week, I'm basically going to come in, bring up the code, and we're going to get to it. So, because I want to make sure that we're good. And by the way, you all now have access to the problems. You can see them in the class notebook. Think of some questions if you got any questions, but we'll just sort of rock and roll. All right, I'll bring up the code. If anybody did not get their exam, tell me. I've got exams here. That's all I got.